So now the point is that now if x and y are projective, see map of projective varieties, they are not globally defined, they are locally defined only. So you have to be little careful. So how do you do that for projective varieties? So now when both x and y are projective, so that is x is some closed subset in Pn and both are in Pm. So how do you define? So what I want x cross y. Yeah, first I want to say that x cross y, I can give a projective variety structure. So that means it should be a closed subset in some projective space. See, but point is that Pn, but the problem here is that Pn cross Pm is not Pnm. This is not true, or n plus m, or which was true in the case of the affine. So how do you do that? Right. So to do that, you need to use something called, which is called Segre embedding. If you, so this is a, so you need to introduce some. So what I want to do, I want to see x cross y in some bigger projective space as a closed subset. To say that this is, and that closed subset means closed subset of some homogeneous, I mean given by some homogeneous polynomial in n plus 1 variable. That's how I should see this product x cross y, and then this is a one-to-one map. Then on this, and on this, I give a map, set theoretic map, x cross y to this bigger space P of n, which is injective. Now on this set, I give a projective. I say that this set is actually a closed subset, zero set of some bunch of homogeneous polynomials. So then automatically that gets a variety structure. I mean, some of course given by some homogeneous polynomial which forms a prime ideal. So then you show that this is so it will be a projective variety. So that's how you give a projective variety structure on this x cross. So you say that this is x cross y, right? But little bit careful that it depends on embedding, because when I did Ax tensor Ay, see x cross y, the A of x cross y in the affine case, I identified the Ax tensor Ay. Once you do Ax tensor, this is a finitely generated K algebra. So this is independent of embedding. Whether you choose x in An or x is a n plus k, I mean, does not matter. See, here I have chosen to say that this x was in An. This is just to, but instead of if I choose A in prime, if x is embedded in some another another affine space, A of x cross y would not change because that's an invariant. So it is independent of embedding. It is just to do the calculation. Ultimately, the finitely generated algebra Ax tensor Ay, this does not depend on the embedding of x in An and x y in An. This is one choice. One choice makes you that this is this. But if you take another choice, you will get another ring, but those two rings will be isomorphic. But the point here is that when you do the projective product, it depends on the embedding, where x is embedded. See, Pn is naturally embedded into Pn plus 1, right? Naturally embedded, because you are just take n equal to 1. So this is 2. So you take this homogeneous coordinate x0, x1. So you just send it to x0, x1, 0. Now one of these coordinate is non-zero, so that will say that this is a map, right? So that's how this is a hyperplane in P2. P1 is embedded. So, but the point is that first that this product Segre embedding, that's why it's called embedding, that it depends on the where your x and y are embedded. The product when you define, it depends on the, it's not independent of embedding. That's a drawback, of course. When if you depend on something, you are, that's not a good thing. But that is it, that's how it is. So morphism of projective varieties is little tricky. So it's always, it's not an embedding free. So that's why in last class I was talking about line bundles and divisors. You need to study those. They are important objects because it gives you an embedding. Anyway, so so now what is it? So let's understand the simple case where P1, so x is say, so let's understand when x is P1 and y is P1, both are P1. I want to give a projective variety structure on P1 cross P1. So first I want to embed P1 cross P1 to some projective space. Okay, so you can do many ways. So you can embed it into P. So this is two variable. So x naught x1 and this is y naught y1. So you send it to x naught y naught, x naught y1, x1 y naught and x1 y1. Now at least one of these xi's are non-zero, at least one of these yi's are non-zero. So that will say this, when you take this product, at least one of the xi yj is non-zero. So this is a map of projective varieties. Check that this is a map of projective varieties. First of all, it's a map. But this is so. But this satisfies some property that if I call this coordinate z naught naught, the first coordinate. If I call this z naught 1, if I call this z1 naught, if I call this z1 1. So then they satisfy some property, right? If I take product, say z naught naught, x naught y naught times z1 1. This is nothing but z naught 1 times z1 naught. And this is this is the only equation it satisfies. And this map is injective. And this is a closed condition. This is a homogeneous polynomial. Take the zero set of this polynomial. Yes, this is a hypersurface, the quadratic equation. So take z to be the zero set of this polynomial. Zero of this. That is a projective variety, and this is an irreducible polynomial. So it will give you a prime idea. So that is the product of P1 cross P1. You define. So this is called. This is also so you are embedding it into. So by this degree 2 polynomials. Well defined means if you take. So what do you mean by well? So that means if we embed it into some other projective space, that is possible. But I am saying this depends on this embed. This is called. There is some reason why I am saying 3. If I, for example, if I take Pn and Pm, I can embed it into Pn plus 1, m plus 1 minus 1 naturally. This is a natural map, right? Given by because. But if so, what is so? This is nothing but n m plus n plus m. So you are embedding it. So now, if you take n equal to m equal to 1, So you go to P3. Right, because the where you are embedding, it depends on number of variables in the left hand side and no other things. Of course, you can embed it into some bigger projective space. That is fine, but this is a naturally you can define. I am not choosing anything else. Only this coordinate, number of coordinates in P1 and number of coordinates in P. So how do you do this in more generally? So this is, you take say x naught, y naught, sorry, x naught, x1, xn, and you take this y naught, y1, ym. Then what you do, you send it to this map, x naught, y naught, x naught, y1, x naught, ym. Similarly, x1, y naught, x1, ym. So and like this up to xm, yn. Hmm? This is the smallest degree such that we can embed. Exactly, yeah. Otherwise, you can make it much bigger, but this is the smallest projective space where you can embed. Yeah, yes. So that is d-tuple. So d equal to 1 here. So this is now the point is that it satisfies some. So if you call this z naught naught, this coordinate z naught naught, if you call this coordinate z naught 1, if you call this z naught ym. So in particular zij, I mean how many I equal to 0 to x n, m or n, this is n, 0 to n and j equal to 0 to m, right. Now you see that zij times zkl is nothing but zkj times zil. Right. So you have such equations and you take the zero set of this homogeneous polynomial. Right. That is the, and now that is a closed subset and it's an irreducible polynomial. It is a prime ideal that generated by this set of polynomials, homogeneous polynomial, degree 2 polynomials. This is a closed subset, homogeneous prime ideal. So that will give a projective variety structure, and that's a yes. Now one can generalize this more. So this is the smallest projective space where you can embed it in your projective this Pn cross Pm. But you can put it into a higher space by choosing, instead of degree 2 polynomial, the higher polynomial, higher degree polynomial, right? Higher monic polynomial, and that is called Segre embedding, d-uple embedding. So one can generalize this. So one can generalize this to embed into a higher projective space, considering. So this is a remark. Maybe I'll do it. I'll give it as assignment problem. that Segre, the d-uple embedding. This is just a generalization of this higher projective space. So this is called d-uple embedding or using embedding. That is because once you have projective space Pn, I can I can put it into some higher space, say Pn, because how you suppose you choose an integer d, okay, and consider degree d monomials in n plus 1 variable. If you have n plus 1 variable and you take degree d monomials, so how many such monomials are there? N plus d choose d, yes. So there are n plus d choose d. So now say call they are m naught up to m. So if you call this capital N, mn, you have these monomials. These are homogeneous polynomials. So I can embed my x naught xn to this m naught, if I call this x, m naught of x, m n of x. And this is a injective map because these are monomials. One of them will be non-zero, right? So this gives an embedding Pn into. So now you first you take x cross y into this image of x cross y. So now what you do? Now you take this x and y, which is a closed subset, you put it inside. So now this is a map. I have not done this exercise, but this is a fact that these are maps are proper. So this x cross y, I can identify the it is with the, so this is image. Image is this under this map. This is the closed subset given by this. Now this is a closed subset. Now Pn, now that closed subset you can embed it into a higher projective space, and map of projective space is a proper map. It takes closed sets to closed sets. So image will be automatically closed. So that is the, so you can embed it into a bigger projective space. But the point is that in this product, so only you have to be a little careful with the projective space, that it depends on the embedding when you take product. When you take x and y are any projective variety, if you just start say, then x cross y is not defined, because you need to first see that where x is sitting inside. X can be sitting inside in a bigger projective space. That may give some other embedding, some other product. You understand? So here you have to be little careful with projective varieties. Which one? N plus d choose d. Minus 1 will be. There are number of monomials, but so that means it's a map to. Yes. So these many variables are there. And then so now you know what is the so this is the point. So the remark, the product x cross y depends on the embedding, where x and y are embedded. Where the affine case it was not. Huh? No, I think n plus d choose d. Number of monomials of degree d in n plus 1. This n plus.
It's like you have to solve like sigma I equal 1 to I equal to 0 to n and I equal to d. So the number of solutions for that is like n plus 1 minus 1 plus d. So like 1 and 1 will cancel.
If you choose d, for example, I think it is correct. Anyway, check. Yeah, check this either n plus d or n plus 1 plus d. I get confused with this. Okay. So now for projective variety, you know, affine variety now you can many times sometimes you have to take product x cross y. But x is affine, y is projective. Still it makes sense because affine varieties are after all quasi-projective varieties. So once you do it for projective variety, you know quasi-projective varieties also. Right, exactly same way you define for quasi-projective varieties. So so it is a product of quasi-projective varieties. So you know then what is product of affine with a quasi-projective, product of affine with a affine, product of quasi-projective with projective. So everything is taken care now. So for now the point is that for pre-variety, when x is a pre-variety, so that means x is some union of some affine ui and y is some union of vj. Ui and vj's are affine. So what you do, you do ui cross vj you define. Now what you do, you have to glue. So there is some gluing information. So you need to glue this ui cross vj with the gluing information given on x and y. Okay, so that is called gluing. I will do, see, once I see I have not done so far. When I define some map from Pn to some x or x to P, or some map from y to Pn, this kind of maps. So one needs to be little careful how to define such map. I will do that once I do this. Then you will see that map to projective space or projective space to something. So see, whenever you have map from Pn to x, so what you do, there is no global map because global functions on projective space are constant. That was done in the last class. So when you say something in the case of affine, it was easy because after all it's given by some polynomial. But here there is no functions from Pn to there are no global functions. So what you have to do, you have to break it into this u0, the standard affine open subsets, and from each u0 you have to give a map from ex. So it's not just one map, it is given by n maps, such that this phi naught on this intersection, each intersection they should match. And now because of the continuity, everything goes well. And not only at the continuity level, at the sheaf level also. It takes the regular functions, so it's a very quite complicated. But this is how you should think, that when you define a map from the projective space to x, you or on each affine piece you have map, and that you hope that those maps glue very nicely so that it gives a map at the projective space level.
Any variety also you can define like this, right?
Yes, I mean suppose you do it for affine, suppose an x is affine, but if now x is any variety, so first you do it from affine to affine, and then you glue this side and you glue that side also. So this is gluing, which is very important in algebraic geometry, and which is quite, you hope first you define at the affine level and then you try to do the carpentry work. You have to fix things, some engineering you have to do, and then you hope that it will it sets up nicely and you get a map. So that's how maps between any varieties or morphism between pre-varieties are defined, and I have not done in that detail. It will become more and more. So it's just an overview. I don't know whether I will do it, but let's concentrate on more properties of morphisms. Maybe I will talk about little bit more about morphism on projective varieties, and then I will talk about the properties of morphisms. So I will stop here.